Hi, let's get into the ideal gas law. Last week we learned about the combined gas law and the other three gas laws that sort of go into it. The ideal gas law addresses the one variable we haven't talked about yet, which is number of moles. Don't need to write all of this. I'll highlight what I think is most important for you. Let's go. We've got, as I mentioned, three of the four major variables: pressure, temperature, volume. We've not mentioned number of moles. No gas is going to be a real ideal gas. We have to make some assumptions. Um, and an ideal gas would perfectly adhere to all the laws that we talked about. But at certain temperature and pressure conditions, like really, really hot and really, really cold and really, really high pressure, really low pressure, it just won't work. The laws don't hold up. But if we assume that an ideal gas exists, it gets us pretty close. And so we use that pretty commonly to model the behavior of gases, which of course are very complicated things. So an ideal gas, unlike a real gas, does not condense to a liquid at low temperatures, does not have forces of attraction between the particles, and it composes of particles that have no volume. Again, none of that's true, but it gets us pretty close for how a gas behaves. So that's what we technically say ideal gas, if you're wondering. The ideal gas law is written below, and you can see that it has four variables: pressure, volume, temperature, and number of moles for any sample of gas. We call it the ideal gas law. It looks like per nerd. And let's go through what every variable means so you're well aware of what needs to go where. Now, the ideal gas law is tricky because the units have to be specific when you plug it in. So you can't just shove in Celsius. You can't just shove in milliliters. The ideal gas law has to be very specific. So on the left-hand side, you've got pressure. For pressure, right here, we go with either atmospheres, millimeters of mercury. Also, that's the same thing as torr and kPa. So it has to be one of those. Then for volume, like I mentioned, has to be in liters every time. So I'm just going to write L for liters. And in case you forgot, 1 liter equals 1,000 milliliters. You'll be converting that a bunch in these problems. N is number of moles. The R is a constant, which we'll talk about in the next slide. It's actually one of three constants. So, all right, one of three constants. And it depends on what your pressure is. So if you use a certain pressure, then you have to use a certain constant, which we'll talk about on the next slide. And then, of course, as you know from last week, the temperature has to be in Kelvin. So, and in case you forgot, Kelvin equals Celsius plus 273. So it's got more rules maybe than some of the other gas laws we were learning last week, but at the same time, I think it's a little bit easier to use as well for solving for things. But everything has to be very specific for it, and this is the one that you don't want to forget, that 1 liter equals 1,000 milliliters, because you're going to be using that a lot. All right, so let's talk about the constant, and then we'll do a couple problems. The constant for R is what we call a proportionality constant. It depends on the units of pressure. So for each given pressure, if you're going to use one pressure, then you have to use a certain R. So for example, if the problem gives you kilopascals, then your R is 8.314. The stuff after that, this stuff right here, that's just the variables, or sorry, the label that goes along with the R. I mean, in this class, I'm not really concerned if you write the label down. What's most important is that you recognize that when you have kilopascals, then that's the R that you use, 8.314. Okay, so then if your pressure's in atmospheres, then you use 0.0821. And for pressures in millimeters of mercury, 62.36, or of course, millimeters of mercury is the same thing as torr. So don't forget, either one of those, you're going to use 63.36. And this goes in for R, depending on what pressure you're told you're using in the problem. And what's fun, if you're solving for pressure, then you get to pick your R. And whatever R you pick, that's what your label will spit out as. So if you're solving for pressure, which of course is this variable right there, and I choose to put my R as 8.314, well, then my pressure answer is going to be in kilopascals, right? Because that's the R for kilopascals. Okay. Same way, if I choose my R to be atmospheres, then my so I put this 0.0821. That's not an 8. Then my pressure answer is going to be in atmospheres, and either one of those is fine. It works the same. They're equivalent. They just have different labels on them. Okay, so that is your R's, and that allows us to get into a couple of these sample problems, which we'll do real quick here. So let's start with kind of your classic one, which says how many moles of a gas are contained in 2.41 liters and 121.325 kPa and 0 degrees Celsius. Okay, you can solve these two ways, and I'll try and show you both. First of all, I like to rearrange them first. I know that's not everyone's favorite, but for this equation in particular, I think it's pretty straightforward. It's not super complicated, and I'll do one of these where I rearrange them and one of them where I don't. So how many moles of gas are contained in 2.41 liters? You could say PV equals nRT. I'm solving for moles right here. That means I'm solving for this variable. I like to rearrange it first, but I'll do that on the next one, I guess. So if you wanted to rearrange it, you would simply, before you even plug numbers in, just divide both sides by R and T and say N equals PV over RT. Then you just shove your numbers in and you're done. But that's not everyone's favorite, and I understand that and I respect it, and I don't judge you too much to your face. I'll judge you behind your back. But okay, so let's just do this one the way that I think you might do it, which would be to plug numbers in directly. So we're using PV equals nRT. The first pressure is 121.325 kPa. The volume is 2.41 liters. That's terrible. That's slightly better. The number of moles that we're looking for, the R, that's a constant, right? And so in this problem, we're dealing with kPa. So if you go back up, you say, oh, kPa, that means I'm using 8.314 for my problem. So that's going to be my R in this problem, 8.314. And the temperature in this problem is 0 degrees Celsius. That's not going to work. You can't put a 0 in there. So you add 273, and of course you get 273 for your temperature in Kelvin. So there's the setup. I think most people, once they get to this step, well, I don't know, I think probably people like to just maybe simplify both sides. So if you did that and you multiplied these two things together here, then you end up with something like 292.39. That's not right. 292.39, and then on this side you'd have N, and then you do this math right there. So you're just going to multiply those together, and you get 2,000, wow, 2,269.72. So this is another way you can do it as opposed to rearranging like I did here. And then you're simplifying both sides, just divide both sides by 2,269.72. And you end up with N equal to some number, 0.129 moles for your label, because that's what the problem's asking for. Okay, so that's one way to do it, is to just simplify both sides, multiply all the numbers you can together until you get a variable that you can, easily deal with. Other ways, of course, there's lots of ways to do it, but that's one of them that I'm showing you there. How about for the nitrogen problem? Okay, for this one, I will rearrange it first just to give you kind of a different view of how you can do them. So what is the volume? So I'm solving for V in milliliters. Okay, and milliliters is going to be interesting because when I use this, remember I told you at the beginning here that volume is always going to be in liters. So when I solve for volume, it's going to spit out liters. I'm going to need to convert it back to liters at the end. So what's the volume in milliliters of 21 grams of nitrogen? Oh, nitrogen's a sneaky 7, by the way, so that's like a little fun wrinkle as well. 32 degrees Celsius, you got to add 273 for your temperature, and 1.3 ATMs. Notice I'm in ATM, so the R I'm going to use for ATM is a different one. I'm going to use this R because that's the ATM for atmospheres. So that's going to be important when we rearrange the problem. So when we solve the problem. So if it's me, PV equals nRT, I'm going to rearrange first. I want to have solve for volume, so I'm going to divide both sides by P, which you probably can do in your head. And you're just going to say, oh, V equals nRT over P. Now you can just shove the numbers in, and there's no need to rearrange the equation. I think this way is a little bit better, but of course, whatever works for you. This problem has some side work as well. Before you can shove the numbers in, your grams have to be in moles. Anytime you see grams for the ideal gas law, you've got to convert them to moles because that's what the equation calls for. So 21 grams of nitrogen, you know the molar mass of nitrogen is 28 grams per mole. And so 21 divided by 28, of course, is 0.75 moles of nitrogen. And that's going to go in for N. So 0.75 moles. The R for atmospheres is 0.08, no, that's bad, 0.0821. The temperature in this problem is 32 degrees Celsius. 32 plus 273 is 305 Kelvin. And the pressure in this problem is 1.3 atm. So if you do that math, 0.75 times 0.0821 times 305 times or divided by 1.3, you get 14.446 liters. Except in this problem, again, it says milliliters right there. So sometimes you got to convert your milliliters to liters to start, and then sometimes you got to convert your liters to milliliters if the problem asks for it at the end. So to do that, we're just going to multiply by 1,000 or move the decimal point 3 spots to the right. And so this answer in milliliters is 14,446 milliliters for this problem. Okay, so quick peek at the ideal gas law. This kind of gives you the basics of it, of the kinds of problems you'll be asked to use. And the major difference, of course, is that R constant, make sure you're using the right one, and also making sure that you have the right numbers plugged in and the right labels when you do that. Okay, this has been super fun. We'll see you soon. Okay, bye.